Welcome to all with Islamic greeting. Assalamu alaikum. My name is Zahidullah Khan. I am student of the 7th semester of Department of Institute of Numerical Sciences of Quad University of Science and Technology. First of all, we will illustrate the outlines of the uh, today presentations. First of all, we will discuss some preliminaries that is required to completely understand the main topic closed graph theorem. After that, we will shortly discuss operators, linear operators, boundary linear operator, product of namespaces, some motivations that why we use closed linear operator. After that, and finally, we will uh, come to the main topic closed graph theorem. Now, we will define what is ball. A given point x not belong to a set x and a real number r greater than 0. We define the following sets. First of all, we will define what is open set. Open set is the set of what is open ball. Open ball is the set of all those points belong to set X. All those points elements that belong to the set X that satisfies this condition. Their distance between 2 point X and X naught less than R, where R is the radius of the ball. And what is the closed ball? Closed ball is the set of all those points that belong to set X that satisfies this condition. The distance between x and x naught less than or equal to r, where in both cases open ball and closed ball x naught is center and r is the radius of the ball. Now we will define open set. A subset M of a metric space X is said to be open if it contains a ball about each of its points. So here we have x, we denote the metric space by capital X, where in the previous slide we use the capital X for the set X for any set, non-empty set. Now open set are those set subset of M uh, which contain all of its points, that a point that contain of its points. Now an example of open ball is in open set. Definition of the closed set: a subset K of the set X is said to be closed if its complement in X is open. So this point is necessary to understand the closed set, that is when we subtract the subset from the set X, so the required set is said to be open, mean the complement between these is open. An example of closed ball is closed set. Now we will define a limit point. We have a subset M of metric space X, then a point x naught of X which may or may not be point of M. It is not necessary that M contain the same point x naught of X is. So actually this point is called accumulation point of the subset of metric M is accumulation point of M, or simply limit point of M if every neighborhood of X contain at least one point, that this point belong to the subset of the metric space X. Distance from the point x naught. So this is the definition of the limit point. Now, the set consisting of the points of M and accumulation points of M is called closure of M, and it is denoted by M. So this concepts is a necessary that we will use in the main topic, that what is closure and closed set. So we denote the closure by the by this notation. So now we have closure. We have some property of closure. Uh, we have a theorem, closure and closed set. Let we have a set M non which is non-empty, and this is a subset of the metric space X, and M dash its closure as defined in the previous slide. Then X belong to closure of the M if and only if there is a sequence Xn in M such that the limit points of the sequence X where X belong to the closure of M. So X only belong to M if these limit point mean X belong to the closure of M. Then we will say uh, M belong X belong to the closure of M. Now the second property is that M is closed. The subset M of metric space is said to be closed if and only if the situation whenever the sequence belong to the subset M as these sequence have a limit point X, which imply that the limit points also belong to the subset of metric space M. Now, the another important theorem, complete subspace. A subspace M of complete metric space X is itself complete if and only if the set M is closed in X. So this is one of the important property of the closed set, that a metric space is said to be incomplete whenever M is closed in X. Now we have a short definition of norm space. A norm space is actually a vector space with a metric defined by norm. Now we will define Banach space. A Banach space is a norm space which is complete a metric space. So completeness is necessary and sufficient for a space to be a Banach. Now we have example of Banach space. Now we have some example of Banach space. So the Euclidean space Rn is Banach space. A unitary space Cn is Banach space, and LP space is also a Banach space. L infinity is also Banach space, and the set of all continuous function continuous function on this interval, generally AB, is also a Banach space. Now we will define what are operators. A mapping from a norm space X. Here X we denote norm space by capital X, into a norm space Y denoted by capital Y is called an operator, i.e. mapping between from norm space to a norm space is called operator. Mapping between two norm spaces is generally known as operator, and we denote this mapping by capital T, where X is the domain of the operator and Y is the range of the operator. Now we have some remarks. We denote spaces by X and Y, operators by capital letter, preferably capital T. As we see in earlier that we define metrics by capital X and capital X. Now here we denote X for norm spaces. So you must remember that whenever X stand for norm spaces or metric space or simply a set, and simply here we denote the image of an X under T by Tx. So you have to remember these notations. Now we have another important definition of operator. Linear operator. Linear operator is actually a mapping between two norm spaces. A linear operator is an operator such that it satisfies these two conditions generally. The domain d of t is a vector space, and range r of t lies in a vector space over the same field. Whenever for all x belong to the domain of the operator and scalar belong to any field, scalar belong to fields, then it is necessary for operator to be linear operator. It must satisfy these two conditions. First condition is that first we take any two arbitrary element from the domain of the operator, then apply operator, and the right side say that first we apply the operator on one of the element of the domain and add them with the uh, second element that we apply the operator. So from both left and right hand side have same results. And the second property say that if we have uh, any any scalars belong to field, if we first we multiply the scalar to the point belong to the element belong to domain of t, then we apply operator r. First we apply the operator on x, then we multiply the alpha. From both we have same result. Now we will define what is bounded linear operator. Bounded linear operator, let we have two norm spaces. One is denoted by capital X and the other is denoted by capital Y. These two are norm spaces, and we have a mapping from domain of the operator to the uh, range set range set mean norm space Y. Let we have a mapping mean we have a linear operators where d of t domain of t is the subset of the norm space, and the operator is said to be bounded if it satisfy these conditions. Mean if first the norm of this image set is less than or equal to the norm of x, c time norm of x, where c is a real number for all x. When this satisfy condition, when the all points satisfy this condition, we say the linear operator is bounded linear operator. So for boundedness it must satisfy these conditions. Now this equation we gave name this equation as equation number 1. And when the norm on the left side is that on the norm on y, this is the norm on y, and the norm on the right side is the norm on x. So this is the norm on x. From equation 1, from formula 1 shows that a bounded linear operator maps bounded set n2 bounded set and y. This motivates the term bounded operator. So bounded is important that we will discuss in our main topic, closed graph theorem. Now we have an important remarks. Our present use of the word boundedness is different from that in calculus, where a bounded function is one whose range is bounded set. So we must have to remember that what bounded means here in functional analysis. Now we have some important properties of the bounded linear operator. The first property is finite dimension. If we have a norm space which is finite dimensional, then every linear operator on X is bounded. It means if we have a finite dimensional non-space, then every linear operator on X will be bounded. Now, the other important property of bounding is continuity, and so later we have a linear operator denoted by T, where domain of T is subset of the norm space X, and xy we already know it is a norm spaces. Then T is continuous if and only if T is bounded. It means whenever T is continuous, it's implied that T is bounded. And on the other hand, if T is bounded, it's implied that T is continuous. Now, the second part of this property say if T is continuous at a single point, then the operator T will be continuous. Now we have another important concept, inverse operator. We have a bounded linear operator from a norm space X onto a norm space Y. If there is a positive B such that mean positive constant, any scalar, such that if it satisfies these conditions, so we say then the inverse of the linear bounded operator exists and it is bounded. But generally when this does not satisfy, so we have a remarks the inverse linear a linear operator or bounded linear operator may not be bounded, so we have to remember this. Now we will define the product of two norm spaces. We have two norm spaces. One is denoted by X and the other norm space is denoted by Y. The two norm spaces, then the Cartesian product of these two norm spaces is also a norm space where the two algebraic operations defined on these two norm spaces satisfy the conditions, these two conditions as usual. So this is a usual. First we add the first coordinate entry with the other first coordinate entry, and the second entry we add the other entry of the second coordinate. So this this we see x plus x2, x1 plus x2, and y1 plus y2. Now the other property says that we have any scalars belong to field, we have to multiply to x and then y. So we see here that we multiply alpha to x and alpha to y. Now the what will be the norm that define what will be the norm that we define on the Cartesian product of two norm spaces? The norm will be like this, that the norm of the order pair Cartesian product of these two, the set of these two will be the set of all those point order pairs. So we say the norm of this Cartesian product is norm of x1. So this is one of the norm, and the norm of plus norm of y, which we denote by 2 y2. So we have an important theorem for any two Banach spaces x and y. Banach, as we discussed, the norm space which is complete is known as Banach space. So now we have two Banach spaces, mean two complete norm spaces. So one is x and the second one is y. So these are complete norm spaces. Then the Cartesian product of these two norm spaces will also be a Banach space. So let's see the proof. So first we will show for any two Banach space x and y, the Cartesian product of these two norm spaces be a set of all order pairs where the first entries belong to the norm space x while the second entry belong to the norm space y, which is also a Banach space. Now we will take in any arbitrary Cauchy sequence in these Cartesian product of two norm spaces, uh, then we write the sequence z in this form because z belong to the Cartesian product, so z have the form. Then for every epsilon greater than 0 there is a positive integer, say n naught, such that for every n greater than or equal to n naught we have this. So mean we apply the criteria of Cauchy sequence. So the difference between the first sequence Zn and the other sequence Zm. So Zn is belong to the Cartesian product of norm space, so it have a form of order pairs. Zm also will be in the order pairs. So this is usual that we subtract how to subtract between two order, how to subtract two norm two order pairs. So first we subtract from first coordinate to first coordinate and the other we subtract two from the other second coordinate. So this is general. Now as we defined earlier that the norm on this Cartesian will be this. So we see here that the norm of this will be x xn minus xm plus yn minus ym, where these two norm both are less than epsilon, some positive number. So we see from here that this imply that this norm is less than epsilon, also this norm is less than epsilon. Now, this implies that Xn is Cauchy sequence in the norm space X, where X is Banach space. Yn is a Cauchy sequence in the complete norm space Y. So now we suppose that the as this is a sequence, so we suppose that it have also a limit, say x, where x belong to the norm space X. Now the yn is also a Cauchy sequence, so it have a limit, say y belong to the Y. Now we will show that z have also uh, limit points which belong to the Cartesian product of two norm spaces. So from these two we can write that the sequence Zn have a limit point z. So we can write in this form that z belong to Cartesian, so its limit will also have this form. So this is usual that how to subtract two order pairs. So the norm of these will be this form, because earlier we defined the norm on the Cartesian product will have this form. Now as n tends to infinity, the norm this norm mean uh, this norm tend to 0 while this norm also tend to 0. So this implied that the limit when we apply n tends to infinity, this will goes to 0. So this imply that the sequence zn have has a limit uh, of has a limit order pair x of y xy which belong to Cartesian product of these two norm spaces. Thus, we are done that the Cartesian product of two norm spaces is also complete, mean it's a Banach space. Now we have some motivation about the closed graph theorem, that why we come here to the closed graph theorem. Generally, not all linear operator in practical importance are bounded. So we see in previous some example that the operator differential operator is unbounded on the interval close interval 0 1. In quantum mechanics and other application, one needs unbounded operators quite frequently. However, practically all of the linear operator which the analyst is like to use are so-called closed linear operator. Now, closed graph theorem, which state sufficient conditions. So, closed graph theorem state sufficient conditions under which a closed linear operator on Banach space is bounded. So, this point is important. Now, we will define the important concept and preliminaries for closed graph theorem is closed linear operator. So first of all, we will define what is graph. If we have two sets x and the other set is y, the mapping between these two sets, say f, the graph of the set of all points order pairs x and f of x in the Cartesian product is called graph. So graph is what? The set of all those points in the Cartesian product is graph of the mapping of the given mapping. Now we will define closed linear operator. We have two norm spaces. One is x and the other spaces. The other norm space is y. So we have also a linear operator mapping between these two norm spaces, where domain is a subset of the norm space x. Then T is called closed linear operator. T is called closed linear operator if its graph, as you see, graph is the set of all order pairs where x belong to the domain of the operator while y is the image of the operator. So one can see that the graph of the linear operator is a subset of the Cartesian product of these two norm spaces x and y, is closed in the norm spaces xy. Mean T is called closed linear operator if its graph is closed in norm space xy, where the two algebraic operation of vector space in xy are defined as usual, as we earlier defined that how to add two order pairs and how to multiply a scalar to order pairs, and the norm that define on these Cartesian product of norm spaces given by this expression. Now we we are in the position to define and to illustrate the closed graph theorem. So under what conditions will a closed linear operator be bounded? What condition when closed operator will be bounded? The answer is given by the imported theorem, closed graph theorem. Let suppose we have two Banach spaces. Banach spaces mean complete norm spaces. One is x and the other is y, and we have a closed linear operator T, where d of t is the subset of the Banach space x. Then if the domain is closed in the norm space x, then the operator T is bounded. So this theorem say we have, first of all, we have Banach spaces, two Banach spaces and a linear operator from domain of T to the norm space y. This say if x domain of T is closed in x, then the linear operator will be bounded. So let's see the proof. First, recall for any two Banach spaces x and y, the Cartesian product is also a Banach space, as we proved earlier that the Cartesian product of two Banach spaces will be Banach space. Now we are in the position to illustrate the other property. Now let's assume that the graph is closed in the Cartesian product. The graph is closed in Cartesian product, hence graph is complete. When it is closed, then complete, because this is a Banach spaces. So g of t will also be Banach. Also d of t is closed in x. Whenever this is closed in x, then as x is Banach, so d of t will also be Banach, mean complete space. Now we consider the mapping p from the graph of the operator to domain of the operator, and define this mapping by p of x tx equal to x. So this is important and we will frequently use to prove the closed graph theorem. Now we prove here three things. First, we will show that this mapping will be bijective, and this mapping will also be a linear. And finally, we will prove that this mapping is bounded. When we prove these three things, then we are done. Now first of all, we will say that p is linear. How? We prove the properties of linear operator, that whenever the operator will be linear. So first we take two order pairs. Two order pairs mean this order pair belongs to the graph of the operator. So we have two order pair belongs to operator. First we apply the uh, first we apply p. So we see as we define here. So we add these two, x1 with x2 and tx1 with tx2. So this is clear by the mapping we define here is x. So here we have x1 and x2. So this equal to this one and this equal to this one. How? Because of these. Now we will prove the second property of the linear operator, which state that we first apply the scalar to the order pair that belong to the graph. Now as we apply, so this is clear, have no confusion usual. So uh, by definition we will write as, and by this definition we will write. So this implies that the mapping P is linear. Now, as P is bounded, because we the norm of this order pair is this. How? Because we define here P of x tx equal to x. So we take norm on both side. Take norm on both side, we obtain this one, and we add the norm of tx. So this right hand side will be greater than to this. Now we will write these two, because the norm of this is this one. So here is one, we can write this, that this linear operator is bounded. Now p is onto, since for all x belong to d of t there exists order pair belongs to the graph of the operator, such that we have this one. P is 1 1. How? We take 2 points from, we take 2 points, P of x1 tx1, P of x2 x2 tx2. So this imply x1 equal to x2 by this definitions. Now this imply x1 order pair and this order pair. How? Because of these definitions. Now, hence P is bounded linear operator from Banach space G of T graph to Banach space D of T, and also it's bijective. Hence, whenever it's bijective and bounded, we can write as we discussed earlier that inverse bounded linear operator. So it is bijective and bounded, given by this mapping, defined by this is bounded linear operator as by bounded inverse theorem. So what is bounded inverse theorem? Bounded inverse theorem said that we have two num spaces, two complete num spaces x and y, and a bijective mapping, a bijective bounded linear operator, then T inverse is bounded. So this is the bounded inverse theorem. That is, there exists a positive number b such that for every x belong to domain of T, we have this one, that the norm of P inverse of x is less than or equal to b time norm of x. So this imply, now what is P inverse of x? We define here. From here we can write this. So the norm of this order pair is num of x plus num of tx. So we defined earlier this, so here we have no confusion. So we can, if we only write this, so this here we have an inequality, other inequality. So from this we can say that uh, the mapping, the image tx is bounded. So this imply the operator t is bounded, hence we are done. So the all of the course content is taken from functional analysis. This one book, some are taken from this, and the last main theorem which I have proved, some of text are taken from the YouTube lecture of Professor Muhammad Tahir. If you have any question, you can email me, then I will answer you. Thank you for listening me.